Good afternoon, everyone. My name is Antonella Ferrara. Probably the majority of you knows me. I'm the chair of the editorial board of UCA, and now my role is actually to introduce the speaker of this semi-plenary section. The speaker is Dr. Jing Zhou. Jing is a full professor at the University of Agder in Norway. She received her PhD from Nanyang Technological University in Singapore in 2006, and then moved to Norway in 2007. She held a different position as senior researcher, as scientist and postdoctoral fellow, and her research focuses on adaptive and nonlinear control, network and learning-based control, in particular with application to offshore cranes, oil drilling systems, robotics, and offshore mechatronics. So please join me in giving the first round of applause to Jing. And I let her the floor.
Thank you, for your nice introduction. So today I will talk about my recent research on adaptive quantized control. We focus on the theories and applications. And before we do the introductions, I will show some motivations. Then we look at the theories. Then in the last, I will introduce some of our research applications by using the adaptive quantized control. So the motivation to study this research is come from 10 years ago when we do the control systems, especially when you have a network control systems. You need to transform information through the networks. Then in this case, you may have limited bandwidth or you may have some processing technologies. Then in this case, how we can compensate this limited information from the control point of view, how we can design the controllers in order to compensate these effects both in the controller design and the stability analysis. And also there are a lot of applications by using the adaptive quantized systems, such as in the industry systems, intelligent transportation systems, and offshore systems. That is the main my research applications. And then we look at how the networks of systems are combined with the quantization and control systems. As shown in these figures, you can see we can put the quantizers into either in the actuator or in the sensor part. And the main advantage to use the quantization is because it is not only inevitable due to the widespread use of this digital process, but also it is very useful for communications, such as in some situations, you want to limit or minimize information flows, or in some situations, due to security reasons, you may not want to send all the information. You only want to send some necessary information. Then the quantization is actually very useful technique. And also in many situations, if you have many systems which are connected through the networks, you need to reduce the communication burden, then the quantization is an important technique. And then we look at the control challenges for these systems. And since the quantization is the nonlinear mapping from the continuous set point to the discontinuous signals, then this quantization will introduce the nonlinearities to your systems. So how we can compensate these nonlinearities and those effects to the system, this is one of the challenges. And also if you have systems, especially in industrial systems, you always have the uncertainties and the nonlinear dynamics. So how we can compensate all these effects together at the same time to design a systematic controller design and doing the stability analysis. That is the most difficult situation. Then for this talk, we will have several questions. So the first question comes to what can we say about the quantization systems? It means that what kind of quantizers and what kind of quantized control system will be considered. So the second question is how we can do and what can we do with the quantization to maintain the closed loop stability and still guarantee the performance as good as possible. So in this talk, I will try to address those two questions. And then we start from the quantization. So what is a quantization? So the quantization is a process of mapping continuous signal to the discontinuous set of points. As shown in these figures, you can see you have this blue curve. This is your input for your quantizer. Then the output is this right, discontinuous signals. And from here, we can easily to see that it is a many to few mapping. It means that for the same output, you share the many input signals. And for this process, it is impossible to reverse its input signal. Then it will come challenges. How we can use these quantized signals to handle the continuous system stabilities. And since the quantization will introduce the quantization error, and this quantization error will be nonlinearity, so we define the quantization error mathematically as a difference between your input signal and your output quantized signal. So we will, based on the quantization errors, to classify the different type of quantizers. So now we look at the different type of quantizers based on the boundedness of the quantization error. So the first type of quantizer, we call this a bounded quantizer. And if you look at this inequalities, it's clear to show that the quantization error is bounded by a constant delta, where delta depends on your quantization parameters. And a specific example for the bounded quantizer is a uniform quantizer. It is very commonly used if you have a unified distributed signals. And also, we can see that for the unified quantizer, you have a unified equal quantization levels, such as here, we have the quantization levels is equal. And as I mentioned, many systems have the unified distributed signals, such as the vehicle control and the robot manipulate control. You have this unified distributed signals. Then for those applications, unified quantizer is an optimal choice to be used. Another type of quantizer is called, here we call this a sector bounded quantizer. It's actually a quantization error is unbounded. So we can formulate the quantization error as this, this inequalities, where you can see that the quantization error depends on the input value, that is your input to your quantizer U, and also depends on some parameters, small delta and large delta is depends on the quantization parameters. So for this type of quantizers, since the quantization error is unbounded, satisfy this inequality, so we call this as a sector-bounded quantizer. And one type of example is a logarithmic quantizers. You can see here. For the logarithmic quantizer, they have the unequal quantization levels. And if you look at the quantization error, it will become smaller when you have the input values close to 0. So many signals have this non-uniform distributed types, such as our audio signals. They are more concentrated in near the 0. So for those type of signals, the logarithmic quantizer is a good choice. And we can also combine the different type of quantizer to generate some new type of quantizer. But before I introduce the new type of quantizer, we look at the quantized signals at those blue lines. And we see that those signals will transmit it directly from one value to another value. And if we consider this part in the controller systems, it actually generates some so-called chattering phenomena. And for the continuous signal systems, we try to have all the system states and functions are differentiable. But if you have this quantized state in your systems, it's actually make your system is non-differentiable. So this is one challenge, how we can compensate this non-differentiable effects and still guarantee your closed loop continuous system stable. And in order to avoid this chattering phenomenon, we can combine the two uniform quantizer with different quantization levels, such as in the left figure. Here we have two types of uniform quantizer, but with different quantization levels. Then we will generate this hysteresis mechanic. And this hysteresis mechanic will generate some delta in order to avoid the chattering phenomenon mathematically. And we can also combine two different levels of logarithmic quantizer to generate this hysteresis logarithmic quantizer, and also generate so-called hysteresis mechanism to avoid the chattering phenomenon. So how we can choose the quantizers is actually depends on your applications and the signals you received from your systems. And here is mathematical formulation of the quantizers. I will not go through details. And then we compare those two types of quantizers. For the bounded quantizer, since the quantization error is bounded from the control point of view, compared to those unbounded quantizer is more easy to be handled in the controller design and the stability analysis. And for the sector bounded quantizer, since its quantization error is based on the input of your signals, is actually unbounded. So the challenge will becomes more even challenge compared to the bounded quantizer. So in this talk, all the following control technologies is actually applied to both bounded and sector bounded quantizer. And if you compare bounded and sector bounded quantizer, we can consider bounded quantizer is a special type of the sector bounded quantizer if you have the small delta is 0. And then we look at what kind of control structure will be considered. As I showed in the first slide, we can put the quantizer either in the actuator part or in the sensor part. Then we will generate the following four different types of control structures. The first type we consider we have the quantizer on the actuator part. It means that the control signal is quantized, then transmitted through the network. Then the actual input to your system is actually the quantized input. So the system, it is called the system with input quantization. So we can also have the quantizer in the output side, that is in the sensor part. We quantize the system states and transmit it through network to your controllers. It means that when you design your controllers, only the quantized states SQ is available. So not all the states are available in your controller design. So this system is called the system with state quantization. Then we can have both input and state quantization on both sides. Then we will have this network. It's called the input and state quantization. And the last structures is for the systems. You don't have all the system states. We only have the output signal. Quantized output signal are available. Then the system is called the output and input quantization systems. So we will look at how we can design the controllers for those four types of control structures. So now we compare the input quantization with the state or output quantization and look at the challenges. So for the input quantizations, since all the system states X are available in your controller design. So when you design controllers, you actually can follow your standard, whatever the control you want to use, state feedback, adapt control, robust control. And the difficult and challenges, you need to compensate the effect from the input quantization. That is the quantization error between U and UQ. And compared to the input quantization, in the state or output quantizations, since you only have the quantized states SQ is available, but those XQ is actually not all the system states X. You actually lose some information. Then the challenge is that how we can use the limited information, but still use the traditional control method to guarantee the stability and keep your system's performance as good as enough. So the challenge compared to the input quantizations, the state quantization is more difficult. So we start from the input quantization, how we can design controllers. So here we use the adaptive control because we consider system has some uncertainties. Then we use adaptive control method to do it. And we consider uncertain nonlinear systems represented as those equations, which is a straight feedback nonlinear systems, where xi is your states and psi and phi are nonlinear functions. And we also have the uncertainty, which is represented as theta, which is uncertain parameter vectors. And the control objective is how we can design a quantized controller such as UQ, which you have only UQ directly go to your systems to guarantee the stability and make your output Y to tracking a reference signal YR. And if we look at those equations in the first n-1 differential equations, there's no quantization in your systems. So it means that the first n-1 steps, here we use a backstepping technique, but if you have different technologies, you can choose different control method. Then we look at the final step, how we can compensate the effects from input quantizations. And then we look at how we could do it. First, the method is based on the Lyapunov technologies. Then we will build the Lyapunov function, including the system state arrow Li, and the parameter estimation arrow theta tilde. And then we do the derivative and get the second equations. And then in this equation, you will have these terms marked by the right color, and the NQU, and QU represent your quantized input. Then we look at, since we want to use the basically Lyapunov method, so then we look at how we can transform the NQU to an explicit function of U. Then if you bring the U outside the quantizer, then you can directly apply your basic control technologies to compensate all unnecessary terms and guarantee the UN dot is negative. Then we look at how we do it. And in this controllers, we develop a special type of controllers. Here we introduce the hyperbolic tangent functions in both U and virtual controllers. And also we do some modifications for the system estimator, theta hat dot, where we introduce a sigma modification in the controllers. And some key technologies are given here. So first, in order to transfer U outside from the quantizers, we use the property of the sector bounded quantizers. Then we can transfer the NQU to this right side of these inequalities. Then we, based on our design the controllers and the hyperbolic tangent properties, then we can show that the NQU is less than a function of the virtual control UN, where UN you can follow the standard controllers to design it. And finally, the stability analysis is based on the Lyapunov functions, and just highlight some part. And finally, I can guarantee the UN dot satisfies the last inequalities. Then we can summarize our result in this theorem. So in this theorem, we show that we can guarantee all the closed loop signals are bounded, and also we can guarantee the ultimate of your tracking arrow is bounded by a constant B1, where B1 is depends on your initial values and also depends on the control parameters. And here we have F1 is in the denominator, means that if I want to improve the performance, I can increase the control parameter CI, or we can decrease the quantization level delta. So this is some result we get it from the controller design. And since in this controller design, we consider we have the stated quantizers, and we can also apply the adaptive control method to do some modifications for the quantizers, such as we use the adaptive estimators to estimate the quantization parameters. Then we call this system a dynamic quantizer, since the quantization parameters is updated online by using this parameter estimation law. So this is the first part when we have input quantization in your control systems. Then we look at the second part, adaptive control for the system-based state quantization. So here we put the quantizer in the state part, means that only XQ can be used in your controller design, as shown here. So we only have the XQ, which is available in your controller design. Then we look at how we can control the same objective, guarantee all the system states are bounded, and achieve the output tracking. And here, we just highlight some challenges. Since we want to use adaptive backstepping technique, if you are familiar with, you will know that for the adaptive backstepping control, you require all the system states and functions are differentiable. And also, but when we use the quantized this, you will have a non-differentiable functions and non-differentiable states. So how we can solve these non-differentiable problems by still using the backstepping controller design without doing any modifications. Then we look at how we do it. Since if you replace the system states by its quantized states, then all this, for example, phi function and psi function is non-differentiable. So in order to calculate these partial derivatives, first we just follow the standard adaptive control. We design your virtual control and final controllers. Then you calculate your partial differentiable of your virtual functions. Then you keep these partial derivatives are not changed and replace all the system states by its quantized states. Means that if you look at the right side of your controllers, you actually have the same formula as a backstepping control. We only replace the states by its quantized states and do some modification on the parameter estimations. Here we introduce the projection to guarantee the parameter estimates are bounded. Then the difficulties come to the stability analysis, how we can prove the stability for your closed loop systems. So before we get to the final result, we establish the first, those two lemmas. And the first lemma shows that the effects of the state quantization on your nonlinear function psi phi and the state arrow Z and virtual control alpha I is actually can be bounded by a function of your Z, where Z is a state arrows. And the second lemma shows that we can guarantee the states X bar, virtual control alpha I, and the final control U are bounded by a function, also the Z. So this is a very important properties. We build the relationship between the continuous function and the quantized function. And then we look at how we can use those properties in the controller, in the stability analysis. So we build the same Lyapunov functions, including your state arrow Z and the parameter estimation arrow theta tilde. And when you take the derivative, do some manipulations, you get the second inequality, where you will find those three blue terms. And for those three blue terms, you will find that it's actually the relation. You get the arrow between the continuous function, alpha nq is quantized function, where alpha n is your continuous function, where input is continuous states. Then we will use the previous properties in those two lemmas, and we can guarantee all these terms is bounded by a function related to Z. Then by choosing the control parameters and the quantization parameters satisfy these green inequalities, we are able to guarantee the V dot satisfy the last inequalities. Then we get the following theorems. And in these theorems, we show that all the closed loop signals are uniform bounded, and the tracking arrow is ultimate bounded by a constants. And also those constants, you can tune it, try to improve your system tracking arrow, such as increase the control parameter and reduce the quantization level. So these are the results for the system-based state quantizations. And then for the third type of systems, when you have both input and state quantization in both sides, you just apply the input quantization technique together with the state quantization techniques to those systems. So I will not show the details for those parts. So we look at the last part. This is the most difficult part since you have even less information. You only have the context output in your systems. And here we just highlight some limited information. Here we only have the context output YQ. And when you do the stability analysis, the input to your system is a context input. And then we try to look at how we can guarantee the stability for your systems. And following the standard controller design, when you have only output signal available, so what you can use the state feedback. First step is design the observers to estimate those unmeasured states. But since those systems, you only have a context states, which is discontinuous, then we will use the non-smooth analysis in your stability analysis. It's called the Phillips solutions to do the analysis. And by design the observers, X hat is an observer to estimate your states, where the X hat, we only use the context output YQ, and L is your adaptation gain L. And at the same time, we design on adaptive controllers where we also use the L, that is the adaptation gain. It means that your controller and your observer are designed at the same time, and they are coupled, strong coupled by each other. And then we look at, here is the final mathematical equation represent observer, controller, and the adaptation. And then we look at the stability analysis. As I mentioned, we use both Lyapunov stability analysis and the non-smooth Phillips analysis to guarantee the stability. And in order to guarantee all the system states are bounded, we introduce 3 types of Lyapunov functions. And the first Lyapunov function is used to guarantee the boundedness of your adaptation gain L. And the second Lyapunov function is used to guarantee the boundedness of the state arrow Z, and also the boundedness of your estimator states. And then the last Lyapunov function is used to guarantee all the rest of the states, such as system states, output, input, and some arrows. And the final theory is given here. We can guarantee the system output is converged to a compensate, like here. So this is the 4 types of context control systems. And for those 4 types of control systems, we can apply to interconnected systems, such as you have many systems which are connected through the network. And then you have some information exchange. Here we can model those systems as here, where you will have this HIG, which represented the interaction between your neighbor systems. So it means that you transfer or exchange some of the information between each subsystems. And then we look at if we have the situations when you have both contactors in actuator and sensor in each subsystems. And the details of the adaptive controller design is not given here, but I just highlighted some part. So to compensate those interactions between the neighbor systems, we use the decentralized control. It means that for each subsystems, you only use your local control signals to design. We are not using the central controllers, but when you do the final stability analysis, you need to build a final Lyapunov function, including all these subsystems together. Then we can guarantee all the systems are stable. Okay, then move to the last part. So look at some applications. So we have applied our designed adaptive context control systems to different types of systems. And the first experiment, we tested the adaptive context controller for this type of helicopter equipment, which is from Cancer. It's called Arrow. And the objective for these systems is to control the pitch and the roll to track sinusoid signals. And here we show some results from the experiments. And the top figure shows the altitude, and your angular velocity can track the sinusoid signal, and the below two figures shows the tracking arrow, and then we can see that the tracking arrow can be bounded in a compact set. And we also compare the results by looking at the total tracking arrow and the total energy, which is actually look at the input for your systems. Then we compare the different quantization levels, where we use the R is actually the number of bits transmitted through the network. If you have a large R, means that you have a small quantization level. Then we compare the different R for the input and output quantizations. Then you can see that we can almost guarantee the similar performance when you have the continuous states by choosing a suitable quantization levels. And we also test this adaptive control method when we have some disturbance to your systems. And then this is the below table shows that those adaptive control method is able to handle some disturbance. So it's actually robust to the disturbance. And the second applications, since you know in Norway, the most industry is oil gas. So all the research, if you apply the research findings, all the research are related to the oil gas. And here we have two different type of applications. And the first applications, we apply the adaptive quantized controllers to the oil drilling systems, such as here we use the adaptive controllers to control the bottom pressure and to maintain it in a certain region. And I just briefly introduce the objective and what is the control problems. So in the drilling system, there's one of new technology. It's called the managed pressure drilling. And this is an adaptive drilling process. Use the top set, choke, and mud pipes to control the downhole pressure within a certain bound. Where we have some limits on the downhole pressure, as I show here in this inequality. So we need to control the downhole pressure larger than the collapse pressure to prevent the wellbore failure. Also, when you're drilling to the reservoir section, you need to make sure the downhole pressure is larger than the reservoir pressure in order to prevent the inflow flow into your wellbore. And also, we need to guarantee the downhole pressure P beat is less than the fracture pressure P fracture to prevent the lost circulation. So those is the control objective. We need to control the downhole pressure PB in this certain range. And the second problem is if you're drilling into a reservoir section, we call the influx of the formation will go into your wellbore if it is a gas. So for those influx fluid, it can be gas, water, or oil, or combination of this. But if in even danger situations, if it is gas, then the gas will expand to the wellbore when it is through the drill strings. If the gas is not controlled in early situations or is not controlled well, it will generate the danger situation. It's called blowout. So then this is a second problem. So how we can detect the CAC, use the control technologies, and how we can compensate and to control the gas in early phase. So we formulate these control problems by just building a very simple dynamic equations. Here we look at systems in drill string part and annulus part. So in the drill string, we build the pump pressure at the first differential equations P dot, represent here. And then based on the annulus part, we build the dynamic equation related to the choke pressure, that is the second equations. Then the some highlight measurements, what can we get for these measurements? So since in the oil gas drillings, you only can get the measurements on the top side. So the downhole measurement is very hard to get it. Even you are able to get it, it has delay and some uncertainties. And then we highlight what are the measured states and what are the unmeasured states. Since you have some unmeasured states here, and then we will use the control technologies to estimate those unmeasured states And here we will use the adaptive observer and the adaptive control to do the controller design. And the control problem is formulated here. First, in the normal drilling operations, I want to control the downhole pressure to reference Pref, which is within this range. And if you have a kick happens, then we will use the adaptive observer to estimate the kick and use the adaptive controller to compensate the kick. So those are the two control objectives. And the detail of the design procedure, you can find it in our reference. And here we just highlight the basic control structures. So we have the two modes of the controllers. In the normal operations, we have actually very simple adaptive P controller plus a flow controller to control the downhole pressure to a reference set point. Once you detect a kick, the kick is detected by using the adaptive observers. Then we will switch to this kick attenuation mode. In this kick attenuation mode, we only use a flow control to make the Q rise goes to 0. So once we are able to make the Q rise goes to 0, we will be able to switch back to this normal operations. So we have this switch mode between two modes. And the proposed adaptive controllers with quantization is verified in this high fidelity drilling simulators was developed by the NOS, that is my previous employers. And here are some parameters. And we compare our developed automatic switch control method with this standard shifting procedures, and here we show the results. And we can see that by using this switch mode adaptive controllers, we are able to make the gas mass as small as possible. This will make your controller and the process more safety. So this is the second operation. So the last operations we have done a lot of research related to the offshore operations, such as when you transfer the load from one vessel to another vessel in the offshore operations, you need to compensate a lot of things, such as motion compensations and the dynamics of payload. Here we use the model-based controllers to build the system model and generate digital twin, and we also use adaptive quantized controllers to control the payload position and to make it to compensate the wave motions. And those controllers we actually tested in our motion lab, as shown in these figures. We have two Stewart platforms. The largest Stewart platform, we mounted a Coma robot on it to stimulate the crane, offshore cranes. Then we transfer load from one Stewart platform to another Stewart platform. Here we have done a lot of research, such as predict the motions for the tool tips and compensate the motion and control the payload positions. And I will show a video. So here is an experiment. We try to mimic the load transportations from one vessel to another vessel, and then we simulate wave motions on two Stewart platforms with different random wave motions. And then you can see that when the ship-to-ship control is active, so we are able to make the payload as follow the small Stewart platform motions. And yes, then I can quickly summarize my presentations. So as you see that we have done a lot of research in the adaptive quantized control, and we also apply to the different applications. They actually have a lot of interest to do other different applications. So if and also the Motion Lab is funded by Research Council. We have a lot of collaborations with industry in Norway. So if some of you are doing the related research and want to do the experiment test, we are open to have the collaboration with all of you. Yes, and then finally, I will show some references. If you are interested, you can find it from the online. So here is the book is covering all what I talked today, and all the references are given here. If you are interested, you can find it online. Then thank you very much. If you have any comments and feedback, send the email.
Thank you so much, Jing, for the really nice and inspiring presentation. As you know, we don't have a moment for asking questions in the session, but of course, you can reach out to Jing during the coffee break, and she will be happy, I am sure, to reply to any question you may have. I ask you to remain for a couple of minutes more. We have the correct amount of time in front, because I would like to invite here and share the podium, or leave the podium actually, to Anna-Sophia Hooks. Yeah. She will tell her name very good. It's very difficult to tell for me, but I tried at least. She is the General Chair of ECC 2026. And so she will briefly present the first, let's say, activity that have been done in preparation of this conference, and give you some information about that. Thank you so much, Anna-Sophia.
Thank you. Hello, everyone. I hope to see you all in Iceland next year. It will be July 7th through July 10th. July 7th will be our workshops day, and then the regular conference for 3 days. I'm going to try to get up our website here. Let's see if, how that works out. The venue is the University of Iceland. We are in Reykjavik, which is the capital of Iceland. You can fly in from many different places, direct flights. Don't remember exactly how many, but it's not very difficult to get up there. I would like to show you some of the dates here. Okay, maybe if someone will help me out, because this is not, okay, I think I'm getting, I think so. Okay. Yeah. Okay, so the first one is September 1. That's when we plan to open for submissions. We plan to have our deadline October 31. And then it goes on with, you know, the regular interval of dates. And some of them have not quite been set yet, but we worked with Antonella on those. Now, Antonella is on our operating committee, together with many other good people. Let me see here. Okay. All right. So this is our operating committee. So there's 21 people on the operating committee. About 10 of them are locally working. So, but otherwise, we have many excellent people from different places around the world. So, my co-chairs are Sigurður Hafstein and Dirk Schäfker, who's with the University of Duisburg-Essen in Germany. Our program chairs are Melanie Zeilinger and Rolf Fintelstein. He was here at this conference. Are you in the audience? Or maybe he had to leave already. And there's our Antonella. Then we come to our NOC chairs. They are both local colleagues in engineering. And then we go on down here. And I won't mention all the names. But, you know, you can take a look at the website and look at it in your phone, and then you can see more information. So please come and bring your friends, and we look forward to seeing you. It's worth visiting. How many people have been to Iceland? Okay, a few, yeah. So please come to our next conference. Thank you very much.
And just to complement what Anna Sofia said, consider that from September the 1st, the paper set summation website will be open for summation. So we hope that many of you will submit papers and join us in Iceland next year. Thank you so much.
Thank you.